Here we have a Ferris wheel that has a diameter of 40 meters. Ferris wheel is a big giant wheel that rotates, and folks sit on the wheel and in little chairs on the wheel, and they go around and around in the wheel and so forth. And so we want to know how fast this wheel would have to rotate so that a rider at the top of the wheel would experience an apparent weight half of their true weight. So if we're looking at the very top, again, we've got the little chair there. We've got a little person that's sitting in the chair, and we want their apparent weight to be half of their true weight. So in this situation, the apparent weight, W apparent, is actually the normal force that the person would feel, right? The normal force is your perception of your true weight. Your true weight is mg. That's the earth pulling on you, and the earth pulls on you whether you feel like you're being pulled on or not, right? Even if you're falling in free fall, you feel weightless, but the earth is still pulling on you, so your true weight is still mg. So what this is saying is that the normal force should be half the true weight. This is the relationship that we're shooting for. If we want to understand what the normal force is of this person, the normal force is a type of force, and so what we're going to do is identify the forces by drawing a circle around this person, maybe more like that, and we'll see that we'll identify the forces acting on the person. They are sitting in a seat, so there's going to be a normal force. That's what we're looking for. And then the only other force is the weight, because they're just sitting there in a chair. There's nothing else that they are in contact with. Also, on this Ferris wheel, they're headed backwards in this case, and they're traveling in a circular path around the Ferris wheel. So they must have a centripetal acceleration pointing towards the center of the circle, and they must have a centripetal force, a net force, acting in that direction as well. We know that by virtue of being on a circular path, you must have a centripetal acceleration pointing towards the center of the circle. We'll go ahead and draw a free body diagram. In this case, our acceleration is vertical, so we'll use vertical and horizontal axes. We'll represent our person as a particle at the center. And in this case, I have a normal force that is going to be pushing upwards on our person. I have their weight that is pushing downwards. Notice that I've drawn these mismatched in size because I know that the centripetal acceleration must be pointing downwards, and there must be a net force pointing downwards. And in this case, the weight has to be the dominant force so that we get that net force pointing downwards. We can use this free body diagram to apply Newton's second law. In this situation, there's really only one direction for us to consider, the y direction. The acceleration, actually we'll do that in the next step. The forces that we have acting here, we have the normal force acting upwards. I've got the weight acting downwards. That's equal to mass times the acceleration. The acceleration in this case is the centripetal acceleration. And the centripetal acceleration is pointing downwards, so I have to make that a negative. This is the magnitude of the centripetal acceleration. We have to account for the direction with that negative sign. In our next step, we can plug in values. And in fact, we can plug in one more value here. The normal force, we said, needed to be half of mg. So now if I have half of an mg and I subtract a full mg, what I end up with is a negative half mg, right? A half minus 1 gives me a negative a half. Notice in this case the m's cancel again. And in this case, we're trying to find the speed of rotation of the Ferris wheel, which a good place to start would be the velocity, let's say. Notice the negative signs are going to cancel out as well. And at this point, I can start plugging in numbers. I know G, and I know R. Another thing here, the carnival has a diameter of 40 meters. And so if I'm plugging in R is the radius. If the diameter is 40 meters, the radius is only 20 meters. And I can plug all that in, and I can find that the speed of the person must be 9.90 meters per second. So that's the speed of the person as they go around. One of the things that we want to convert, though, is we are asked for how fast in RPM. So RPM is revolutions per minute. So that's also a sense of speed, but we need to convert here. So what we have is 9.903, let's say, meters per second. Whenever we're doing one revolution is once around the Ferris wheel. And so the distance that we're traveling then is going to be 2 pi r. It's going to be the circumference of the Ferris wheel is going to be that many meters. And so we can cancel out meters that way. If we want revolutions per minute, well, for every 1 minute, we're going to have 60 seconds. And so I can convert seconds that way as well. And I can put all this together and find the speed to be 4.73 revolutions per minute, or RPM. The second part of the question asks, at the same speed as part A, what would be the apparent weight at the bottom of the motion? So at the bottom of the motion, the chair would be here. The person would be sitting in the chair there. Their velocity in this case we just found would be 9.90 meters per second. And if they're going around a circular path, we know by virtue of going around a circular path, you must have a centripetal acceleration. You must have a centripetal force, a net force causing that centripetal acceleration, and those have to point towards the center of the circle. That has to be the case by virtue of being on a circular path. So same as before, we can draw the circle around the person, figure out the points of contact. We see that there's normal force and weight acting again in this case. We can go ahead and draw another free body diagram. Again, everything is vertical and horizontal, so we'll use the same for our axes. Again, we'll represent the person as a particle. And in this case, we're going to have the normal force acting up, the weight acting down. And in this case, the difference is that the acceleration points up and the centripetal force points up. So notice the normal force should have been a little bit bigger here than the weight. The weight should technically be the same size as it was before because it's the same person, but the normal force should be bigger to give us the acceleration here. So now we can use Newton's second law. That's the point of a free body diagram, is to set up Newton's second law equations. In this case, again, everything is just in the y direction. What I have now is normal force that's going up. I've got weight that's going down. I've got my acceleration in the y direction is my centripetal acceleration. That is upward, and so that's going to be in the positive direction there. I'm looking for my normal force. That's the apparent weight. I can plug in the other values. And in this case, I can find this. That, recall here, mv squared over r was 1/2 mg, and so this mv squared over r is going to be 1/2 mg as well. And so if I have an mg plus another 1/2 mg, then my normal force is going to be 1 plus another half is going to be 1.5 mg, or we're going to feel 50% heavier at the bottom.